Okay, so we're going to work problem 29.25. You can see in the picture that we have a rail between the points A, C, B, and D. It's going like that. Okay, there's our rail. And then we're going to have a bar that goes this way. And they tell us some stuff about it, like they tell us the magnetic field that's inside of it is there. Okay. And they tell us that's perpendicular to the plane of the page. And you can barely make it out, but it looks like it's going into the page. It says perpendicular to the plane of the page. So it's moving into the page. So it's like little X's. You can barely see them in the picture like that. So those are the actual magnetic field. Okay, I'm gonna get rid of that ugly thing. Oops, sorry. Okay, so, and then we're gonna figure out, they want us to find the magnitude of the EMF. Okay, that's gonna act on it. And we know that E is gonna be the magnitude of V, B, L, where V is gonna be the velocity. So it's going to be in meters per second. Well, that's not the magnitude, so we don't have to care about that. Really, it's going to be the absolute value of that. So it's going to be just the 7.5 meters per second. And it's going to be the 0.8 Tesla. And then it's going to be the length of it. They give us 50 centimeters, but it's 0.5 meters. So our units are Tesla meters squared per second, which we saw earlier was going to be a unit for volts. And our actual number is going to be 7.5 times 0.4, which should be 3, or 3 volts. Okay. So that is going to be our answer, 3 volts. Okay. Then they ask us, I'm going to check it to be sure, because I'm pretty sure. 7.5 times 0.8 times 0.4. Oh, I'm wrong. It's 2.4 volts. So this is actually not 3. It is 2.4. 2.4 volts. Check that again. 0.8 times 0.5 times 7.5. No, I was right the first time. It was 3. Ugh. Okay, so that is 3. And this is also 3. So that's part A. Part B asks us to find the direction that the current flows in the rod. Well, we have so for B, we know that the flux is increasing, and that the field comes out of the page, goes into the page. So that means that the induced field, to oppose that change, has to go into the page, out of the page. And what that means for us is that if I grab the wire there, in order to get a field inside this area that goes out of the page, that opposes that direction, the only way I can get that, my thumb points upward. So I'm going to get a current that goes around like this, and that's going to be a counterclockwise current. Okay. Now, for C, they say that if we assume that, let's see, if the resistance is assumed to be constant, okay, they don't know the force that it takes to move it along there. Well, this is kind of an interesting problem, because we know that the force, like, we're going to take a charge, we're going to take basically we're taking this bar, a whole set of charges, and we're moving it through a magnetic field. Well, the force on a current carrying conductor, we know that. It's going to be IL cross B. And since the direction V is going to be perpendicular to our magnetic field, we can just solve for it by finding ILB. But we have a problem, which is that we don't know the current, but we do know the voltage from up here. So we can find it by taking E over R times L times B. So we can take our 3 volts, divide by 1.5 ohms, times our 0.5 meters, times our 0.8 Tesla. We multiply all that together, we should get 0.8 newtons. And we can verify our units if you like, because we get volts over ohms. That's going to be amps times meters times Tesla. Amps are coulombs per second. Meters. Tesla is I'm going to erase that, is a Newton seconds over coulomb meter. So those go away, and those go away, and I'm left with just newtons for that. So that's C. Okay. And now we're going to go on to D. D says they want us to compare the rate at which mechanical work is done, F times V, to the rate at which thermal energy is developed in the circuit. So we're going to do 2 calculations here. We're going to do F times V, which is going to be the 2 answers we have. FV is going to be our 0.8 newtons times our velocity, which is 7.5 meters per second. That's going to give me 6 Newton meters per second, or 6 watts. Okay. And then the other one we're going to do is I squared R. That's going to give us our rate of power. So I squared R. Well, we found I over here. That was 3 divided by 1.5, so that's going to be 2. So 2 amps squared times our resistance, which they gave us in the problem up here, 1.5 ohms. So 1.5 ohms. It's 4 times 1.5. That's 6 watts also, which is good. We should be using the same amount of power both ways. The amount of power that we get in the circuit should be the amount of mechanical work that we did. It's 100% conversion, the best kind of conversion. And that's really all I have to do to do 29.25.